Hello, today we're going to discuss solving circuits using phasor analysis. So to begin, let's start with a motivational problem, in which case we'll just start with a simple RC high-pass filter with some voltage in with a capacitor and a resistor, and let's say we want to find the voltage out. If we were to begin by writing a KVL loop around here, we'd have that minus V in plus 1 over C times the time integral of the current through the circuit plus this output voltage would equal to 0. And we know that we have this time integral since the current through the capacitor solves a differential equation where I is equal to the capacitance times the time derivative of the voltage. Another sort of mitigating factor is the fact that C has a frequency-dependent resistance, as we'll call it now, or some flow to current which is dependent upon the input frequency. So taking all of these together and recognizing now that our KVL solutions now have integral and differential equations, we begin to notice that solving these differential equations, while it might be relatively easy for this circuit, becomes non-trivial when we start doing more and more complex circuits. Even adding extra nodes, one extra node, would drive the complexity of this circuit up quite a bit. In that instead of solving systems of algebraic equations, we now have to solve systems of differential equations. So the motivational question here is there a way to make this any easier? And furthermore, we've up until now mostly considered sources which were DC input sources. But a DC signal is simply a signal with frequency 0. What do we do with all the other signals which have some frequency-dependent nature? How do we handle those inputs? So to begin to answer that question, let's begin with a simple case. So let's look at, again, an RC high-pass filter, except we've added in a switch and an AC source. Typically when we would solve these capacitive circuits, we'd shut the switch down and then calculate the differential equations at the transient and the steady state. The transient right when the switch closes, and steady state when the switch has been closed for some amount of time. Now, let's give ourselves an input which is now a cosine function with some frequency omega, some phase phi, and some amplitude a. What phasor analysis allows us to do is analyze this circuit and, importantly, convert these differential equations into more simple algebraic equations at the steady state. So when we're doing phasor analysis, there's an implicit switch, but that switch has been closed for long enough time so that the signal can reach its steady state where we'll see a sinusoid propagating through this circuit. So how can we make this easier on ourselves? How can we turn differential equations into algebraic equations? So let's begin with the fact that RCL circuits, that's resistor, capacitor, inductor circuits, are linear. And what this linearity means is that the frequency that we feed in is the frequency that we feed out. The only thing that changes in this linear circuit then is the amplitude and phase. So we only need to keep track of these two values and not the frequency. So how can we do this in an interesting way? Well, we can encode these values, in this case the amplitude and the phase, into a single number. And the mathematical framework that we're going to use to do that is a complex or imaginary number. Just a side note, I really don't like the word imaginary. Complex number, I feel, describes what we're doing more succinctly, since imaginary implies that these values don't exist. But the values of amplitude and phase are measurable and do exist. So you'll hear me calling them complex numbers, but if you've only encountered them as an imaginary number, it's the same thing. So this all comes from the fact that we can apply transforms using Euler's formula, which allows us to relate complex exponentials to cosine and sine functions. The math of this full transform we'll deal with a little bit later. Here we'll just see how we can use this to solve these problems easier. But let's get an intuition on what it is that we're looking at. Let's say we have two sinusoids. One sinusoid is going to be a reference sinusoid, this blank line sinusoid, while the other sinusoid is the sinusoid that we might measure, the dotted line. The phase is simply the distance in degrees from peak to peak between the two sinusoids. Now, as a note, whenever we're doing phasor notation, our reference will always be that of a cosine of phase 0. So we'll always measure all of our signals with response to that. So, where do complex numbers come into play here? Well, like I said, we can encode the amplitude and the phase onto a single complex number. So let's look at a 2D axis where we have the real numbers on the x-axis and the imaginary numbers on the y-axis. So we can realize that a cosine, for example, at some amplitude and some phase, can be represented as a complex number where we have some radius into some space here. This radius would correspond to the amplitude, and the angle with respect to the x-axis can represent the phase. So we can begin to write complex numbers in terms of their amplitude and their phase. But notice also something kind of interesting here, that if instead of looking at this in a polar sort of way where we're looking at a radius and an angle, we can also look at this as a rectangular way, where we have some value that is a component on the x-axis, let's call this A, at point A, and some component on the imaginary axis B. So we can also represent this number as a point in the rectangular space of this complex plane of A plus JB. Now, in math class, you may have seen the imaginary number written as I. As engineers, I typically means current for us. So we substitute that and say that J is equal to I, and just a reminder that J is simply the square root of -1 as a complex number. So we are able to look at these signals in two different ways, but it carries the exact same information. We can look at it in terms of an amplitude and a phase, or as a point on the complex plane. And again, all of the information here is conserved as we move between them. And just a couple of helpful formulas, like I said, they encode the exact same information. So we're able to move between these two values with a couple of relatively simple mathematical operations. So let's say that we had some complex number A plus JB, and we wanted to move it to the polar notation of C at an angle of D. Well, we would just simply write the real part here, and this is the imaginary part. The real part and the imaginary part together as a Euclidean distance. So a squared plus b squared, the square root of that, would give us c. And then we can compute the phase by simply taking the arctangent of b over a. Likewise, if we have some number that is represented as an amplitude at a phase d, well, using this relationship, we can simply convert that back into a rectangular complex number. And again, that's all coming here from Euler's formula. So if you wanted to dig deeper into that, you absolutely could. So again, these two complex numbers contain the exact same information. We're not doing anything to augment the numbers. They're just two representations of the same value. And these are collectively known as phasors. Again, the important part here is that in these circuits, because the frequency is preserved, we only care about the amplitude and the phase. And our phasors are just complex numbers which encode for both amplitude and phase. But we have two different ways of looking at that. So again, all we're doing here is just encoding our input signal as well as our other circuit elements in terms of their amplitude and their phase. So how might we use these phasors to solve individual circuits? Well, I broke this down into several different steps that we can use. And then we'll walk through a couple of circuits in doing this. So step one, we want to transform our inputs into a phasor. So in this case, we'll oftentimes have a cosine function with some amplitude, with some frequency, with some phase. So we'll do that conversion. Now luckily, this we can just pull out directly. So let's say we have an input cosine which has 5 as an amplitude, an omega of 1000, and a phase of 31, let's say, plus 31. Then we can do that transformation on the input by simply taking the amplitude and the phase. And we've done that transformation. Step 2, then, with the rest of our circuits, we'll want to take our impedances and turn them into phasors. So the way to look at that is, remember, up until now, we've been using the terms resistance and impedance interchangeably. And this is the case when we're dealing with purely resistive circuits. But we also want to account for the frequency-dependent circuits. So we have a new concept of impedance, which is simply Z, which is the impedance, is equal to the resistive portion plus the complex value of what we call the reactance. And so the reactance is going to be largely due to capacitors and inductors. Now, in lab, we haven't talked too much about inductors, but we'll see they're not that big of a deal when we start solving circuits here. But these correspond to the frequency dependence terms and the reactance, while this is the frequency independent resistance. So now our idea of impedance now not only consists of just resistors, but also our reactive elements, the capacitor and the inductor, which you can loosely think of as the frequency dependent components. So to do these transformations, because this is frequency independent, the transform of resistor, so to convert resistor value into its corresponding impedance, well, it's just simply the resistor value. So that is going to be relatively straightforward. Now remember, when we were talking about the capacitor, it is now frequency dependent. So we have to do a transformation that takes into account the input frequency. So in this case, this is going to be 1 over j omega c. Sometimes you'll see this written as j2 pi f. Personally, I like this notation for reasons that will become apparent when you go into ECE 301 and study signals and systems, but you'll oftentimes see these. These are interchangeable. And the transformation for an inductor, likewise, is simply j omega times L. So we do all those calculations in the circuit and replace those our component values with these transform values. Step number 3 is to convert all phasors to a single convention. Because what you'll notice here is that when we calculate our phase representation of our input signal, it will oftentimes be as a polar representation, meaning an amplitude at some phase. However, when we calculate these, they'll most often come up in a rectangular formulation, which is something on the order, or something that looks like A plus JB. So we'll need to get these into a common language so that we can do operations on them. So that would be step number 3. Step number 4, this is the beautiful part. We can solve the circuit now as normal, and notice how the differential equations simply become algebraic equations, meaning that we can use KVL, KCL, node voltage mesh current method, we can do Thevenin and Norton equivalent circuits. All of the tools that we've learned so far are now back and available to us, so we can solve the circuit as normal. And the last step is if the question or the value that you're trying to solve for is in a different complex number form, just to convert that back. Now, a couple of last minute notes here. Whenever we're in phasor notation, Ohm's law still applies. We've switched the switched the R here for a Z, so that voltage most generally equals the current times the impedance. Series impedances, when we've done the phasor transform, they add just like series resistors do. And parallel impedances add just like parallel resistors do. Now, this is the case once after we've done the phasor transformation and not before. But once we got the phasor transformation in, these values hold. So again, there's some notion that we can still keep doing the same things that we've been doing all this semester so far, and do them just as easily. So let's look at a simple problem to begin. So if you haven't seen it, this circuit element here is the inductor. The inductor solves the differential equation. The voltage is equal to the inductance times the time derivative of the current. You can think of this as a dual of the capacitor. But the kind of beauty is we don't have to worry about the dynamics of this because we have our nice phasor transform that will make us be able to treat it just like a resistor. So let's start by looking at our input here. So we've got an amplitude of 750, and so our omega, our frequency, is 5,000, and our phase is equal to 30 degrees. So the goal of this problem is we want to find I, the circulating current through this circuit. So step one, let's convert our input. Vn will simply be the amplitude at an angle of 30 degrees. So 750 at an angle of 30 degrees. Excellent. Okay, so now let's do step two, where we convert all of our circuit elements into their respective impedances. So starting with the resistor, because that's the easy one, ZR is simply 90 ohms, the value that we're looking for. Okay, and then our inductance, again, remember it just follows the formula of J omega L. So that's simply J times our omega 5,000 times our inductance, which is 32 times 10 to the negative third. And so if we crunch that out, that would get us J 160 ohms. Just a note here, sometimes when you're dealing with a purely complex or a purely real number, you can realize that this is the same thing as saying 0 plus J 160, and this resistance value here, as it's purely real, is really just the same thing as 90 plus J0. Sometimes it helps to think that way because a common mistake is to think that you're trying to solve for J, or that you can't do operations between purely real or purely complex numbers. You absolutely can. And this sometimes will help you see that you can add these two numbers just fine. In fact, we'll do that here in just a moment when we find a series resistance. So let's carry on with finding ZC. In this case is a little bit more complicated, but nothing that we can't handle, with 1 over J omega C, which is equal to, and you can prove this to yourself here. We can pull out the j from the denominator, which makes our numerator negative. Again, it's helpful to have a list of properties of complex numbers when you're going through these problems, so that you can get used to the manipulation of complex numbers, because that takes a little bit of practice, but hopefully we'll give you a lot of that here. And in the denominator, we have omega c, which is just equal to minus j over 1 times 5,000 times, we have 5 times 10 to the negative 6. And if you crunch that out, you'll end up getting minus j 40 ohms. So it is at this point that we have our new complex impedances that I like to redraw the circuit to reflect this. Sometimes it helps to have just visual reminders of what is happening, so let's go ahead and redraw the circuit. So we have an AC voltage source here that has an input of 750. I didn't give myself enough room here, about an angle of 30. So hopefully you can see that here. And then for now, I'm going to replace these as boxes corresponding to impedances. So this box corresponds to this resistor up here, which is just simply 90 ohms. Then I'm going to replace the inductor with a box, and this box has a characteristic impedance of J 160 ohms. And then I'm going to do the same thing and replace the capacitor with another box here. This time is just going to be minus J 40 ohms. Now, oftentimes, and in the next problem, I'll just keep the components as they are. But sometimes this helps to see that really these are all just impedances. It doesn't matter now that we have a resistor, an inductor, and a capacitor. They're all now, if I may use the term, speaking the same language because we've transformed them into an impedance space. Okay, so now let's go ahead and do step 3 and make a conversion so that we can have all of these in a unique term. But first, let's recognize something important here, that around here is a series connection of elements, meaning that we can simplify this as a single impedance, because they're all in series, as simply 90 plus J160 minus J40. So this corresponds to the resistor, the inductor, and the capacitor, and they're all in series. So that gives us an equivalent resistance of 90 plus J120. Okay? So again, the algebra is coming from the notion of algebra on complex numbers, so it might be good to review that as well as you're solving these problems. And we'll see some more examples of some nice things that we can do here. So now we're getting somewhere, because if we want to solve the current through this, we need to look at the current through all these elements, and we can lump all of these elements together, and then it's just simply Ohm's law that we have to use. But first, let's convert this equivalent impedance into polar notation, because this is in polar notation. That will make our algebra easier to do. So let's do, and that I called step 3. So let's go ahead and do that. So since ZEQ is equal to 90 plus J120, let's go ahead and do the math here. So we're going to have C is equal to the square root of the real part squared, so 90 squared, plus the complex part, 120 squared, which then, if we do this, gets us a value of 150, and then d is equal to the arctan of 120 of the complex part over the real part, so 120 over 90, which then gets us, if you do that math, 53.13 degrees. So now we can write this equivalent impedance as 150 at an angle of 53.13 degrees. Now again, by doing this conversion, I haven't lost anything. I am in fact giving the exact same information. It's just now the input and the equivalent impedance are in the same notation, so it's going to make the math easier to do. Now to find this current, we just simply need to use Ohm's law, and this is step 4, where we're just solving the circuit as normal. So we know that V equals IZ, so I is equal to V over Z. And so our V here, remember, is just our input here. So 750 at an angle of 30 degrees over our impedance, 150 at an angle of 53.13 degrees. Now, I'll have you prove this to yourself, but just a reminder that when we're looking at doing division with polar notation, these two values will divide as normal, and these two values will subtract. If we were multiplying, these two numbers would multiply, and these two numbers would add. But here, since we're dividing, we divide this by this, which then gets us a value of 5, and we subtract these two values. So 30 minus 53.13, so that gets us at an angle of minus 23.13. And haha, we have solved this circuit using phasor notation. We don't need to do step 5 because we've got this into a proper form. Oftentimes, voltages and currents are represented as in polar notation. Oftentimes, the impedances are represented in rectangular notation. But again, no information is lost by doing one versus the other. So then we could convert this back into the real domain, the time domain, and realize that our current is going to be some function of a cosine with amplitude 5 and angle minus 23.13. So our current in time is going to be 5 times the cosine of 5,000 t minus 23.13 degrees. And there we go. And so that's our first problem to solve. And notice again here how we turn differential equations into simple algebra equations, and we can carry on using the same circuit analysis methods that we're used to. The only difference is just that we're using complex numbers. So let's move now to a much more complex circuit. So this one is going to be quite tricky. So what I would like you to do, though, is to pause this video and give this an attempt. I want you to see if you can't solve this circuit. So with this circuit, we're looking for all the branch currents. So I want you to solve for IA, IB, and IC. Notice here that we've got a dependent source, which is a function of the current through here, IX. So we'll probably also want to solve for IX as well. So I want you to go ahead, pause this video, and give this a shot. All right, so let's begin to solve the circuit, and let's start with step number 1, in which we can convert our input sources into phasor notation. So we notice that we have our input current is a cosine function with an amplitude of 10.6 with an omega equal to 5,000 and this time a phase that is simply 0. So then we can write this IN as 10.6 at an angle of 0 degrees. All right, let's move now to step number 2, where we do our conversions of all of our circuit elements. Now, we know the resistors are just going to stay the same. So all we really have to worry about converting is the inductor here and the capacitor here. Also a note, the dependent voltage source will behave just as other dependent voltage sources do, so no direct transformation is necessary because the transformation will occur as we solve for Ix. It will already be in the phasor notation form. So we don't need to do anything there. So let's first look at the inductor. So we have our ZL is equal to J omega L. And so we've got an omega of 5,000, an inductance of 0.4 millihenries. So that will simply be J times 5,000 times 0.4 times 10 to the minus 3. All right, so then that is just equal to, let's see here, J 2 ohms. Okay, now we'll do the same thing for the capacitor. We'll do its transformation, which, just as a reminder, is 1 over J omega C, which is equal to, we'll do a little bit of conversion here, minus J, again using the properties of complex numbers, 1 over 5,000, our frequency, times 40 microfarads, so 40 times 10 to the minus 6. And doing that math gets us minus J 5 ohms. Okay, and again, just as an intermediate step, I always find it helpful to redraw the circuit with our new impedance value so that we can start drawing all over it. We've got everything transformed here, so we'll start with a current source. That is going to have the value of 10.6 at an angle of 0 degrees amps. This time, I'm going to keep all the components the same. So a resistor will look like a resistor, capacitor will look like a capacitor, inductor will look like an inductor, but the phasor transformations have already been performed. So again, as we're transforming our resistance value, it just stays the same. So that's going to remain 10 ohms. This resistor up here is going to remain 1 ohm. This inductor, however, that is now going to have a phasor representation of J 2 ohms. Okay, then let's go ahead and get this capacitor here. This capacitor will now have a value of minus J 5 ohms. And then this resistor here have a value of 5 ohms. And then we'll just add in our dependent source. I should note here, whenever you're redrawing these circuits, if you want to use the component notation like I'm using here, go for it. If you want to use the box notation that I used in the previous problem, if that's more helpful for you, then absolutely do that. Just whatever makes solving these circuits easier for you. So it comes down to solving a lot of these problems and experimenting. Okay, so whenever I see a circuit like this, the analysis method that screams at me is node voltage analysis. And that's because we have a large reference area where much of the branches connect to, all of the sources connect to. So this makes a fairly logical ground. And we have two well-defined nodes here. So you could solve this using any of your favorite methods. You could brute force this with KVL, KCL. You could use a mesh current analysis. That would work as well. Sometimes mesh current is nice when you have current sources, but for now, let's just use node voltage. And the reason why I'm going to use node voltage is just to prove to you that nothing changes with the method. The only thing that's changed is that we're now doing operations on complex numbers. But node voltage remains node voltage, mesh current remains mesh current, Thevenin equivalents remain Thevenin equivalents. The only thing that's changed is that we're operating on complex numbers in the frequency domain as well. So let's call this node node 1, this node as node 2, and let's place a voltage value here that is V1 corresponding to node 1, and a voltage value here, V2, corresponding to node 2. Now remember, with node voltage, we really want to follow the passive sign convention, so we'll draw some signs here. And the reason why we're drawing signs with a plus and a minus in this orientation is that in this problem we've already given that the current is moving this way, so we always want it to move from positive to negative. So that's the orientation that we will follow. So this is Ix. Then all the rest of our currents remain. So the first thing that we want to do with after we've assigned all of our nodes is just to start writing out some KCL equations. So let's start at the top and do KCL at node 1. So at node 1, we've got this source current flowing in. This current that is going to flow out this way, and then this current that's going to flow out as well. Again, it doesn't really matter how we define it as long as we are consistent with our directions as we solve the problem. So KCL at this node would simply be the currents entering and the currents leaving. So let's write that out. So we're going to have minus IN, and I'm doing minus because all these currents should sum to 0, so the current entering the node should equal the current leaving the node. So because it's entering and the others are leaving, I'm going to mark it as negative. Then we're going to add in the current going down this path, this resistor path, but that is simply going to be, by Ohm's law, V1, the voltage across this resistor, divided by the resistor value. And that's a current by Ohm's law with respect to impedances. Okay, and now we have to account for Ix. Notice something here. We've got a series connection of an inductor and a resistor. So this equivalent impedance is just equal to the sum of these two. So that is simply going to be 1 plus j 2 ohms. So if we wanted to, we could replace this as one big block, but this is the equivalent impedance. So the current Ix is just simply going to be the voltage at this node minus the voltage at this node divided by this impedance. So V1 minus V2 divided by 1 plus J2. And all this is going to equal 0 as well. So, okay, so let's start cleaning this up. We know that we have two unknown voltages at these nodes, in this case V1 and V2, so that we know that we're going to need another equation, which we'll get from KCL at this node. But for now, let's get everything in terms of our two unknown variables, in this case V1 and V2. So to do that, let's multiply by 1 over J2. And so that will get us, let's see here, minus 1 plus J2, and then this input current is simply 10.6 at an angle of 0. Again, we've got mismatching notation here. We'll deal with that in just a second. We'll do that conversion. But let's write out the rest here. So we're going to have plus 1 plus J2 times V1 over 10. And then the reason why we multiply by 1 plus J2 is that we get this V1 minus V2 value by itself, which is going to end up helping us quite a bit. So V2 is equal to 0. So let's deal with this conversion. This one actually becomes quite easy because if we were to do the math, let's just say over here, remember to get from polar to rectangular, we would simply say 10.6 times cosine of the phase angle plus J sine of the phase angle. And boom, this just becomes 1. This goes to 0. So then to convert this to rectangular form, it simply drops out to be 10.6 with an implicit J0, but we can just let that go for now. Okay, so drawing this out and doing the math gets us then minus 10.6 minus J 21.2. Again, if you want to convince yourselves of like the property of multiplication with complex numbers, you can go look up tables here. Again, that'll be quite helpful as you're practicing these problems and preparing for problems in the lab or in class. Plus V1 over 10 plus J V1 over 5 plus V1 minus V2, all that equals 0. So now what we're going to do is collect the terms of V1 and V2. So we can do that just by simplification, and we'll find that V1 times 1.1 plus J 0.2 minus V2 equals 10.6 plus J 21.2. Okay, so now we're starting to get somewhere. So we've got two unknowns, means that we need two equations. So the next logical point is let's just do it at this second node. So we'll do KCL at node 2. So that will be just this branch here. So we already have this IX current coming in. We'll have a current going down this capacitor branch to ground. And then we'll have this current leaving this node as well. That is a part of the dependent source and through this 5 ohm resistor. So let's write that out. So KCL at node number 2. Well, the first one we've already done. So we know that's going to be V1 minus V2 over 1 plus J2. Again, that's just this current through this series impedance here. And because it's currents entering versus currents leaving, we'll set that equal to V2 over minus J5. Again, get this into the camera view, but V2 over minus J5, I intentionally write the minus sign just so that you know that we're, minus sign down in the denominator, just so that you know that we're just dividing by the impedance here. Then we'll add in, this next node will simply be the voltage at node 2 minus the voltage at this particular node associated with the dependent source. And we know that the dependent source has a voltage of 20 IX. So let's go ahead and write that out. So that will be V2 minus 20 Ix, and then we're going to divide by the impedance in that path. So that's just going to be 5. Okay, now that we have our KCL at node 2, let's go ahead and sub in for Ix. So to account for the dependent source. So we know that Ix is going to be equal to V1 minus V2 over 1 plus J2, which then gets us our KCL at node 2 as V1 minus V2 over 1 plus J2 is equal to minus V2 over 5 plus V2 minus 20 V1 minus V2 over 1 plus 2J, or sorry, J2, all that over 5. So the problematic part is probably going to be this value here. So let's deal with that by multiplying by 1 plus 2J. So we'll multiply both sides by 1 plus J2. And doing that clears things up a bit. So this ends up going away, so we just have V1 minus V2 is equal to, we can deal with this as 1 plus J2 times V2 over J5. Notice that I've taken the negative sign and put it out front here. That's just for my convenience, really. You can handle that as you would normally like. Then 1 plus J2 times V2 over 5. I'm separating out these values so that I can just simply write 20 times V1 minus V2 over 5. And check that out. Now we've gotten rid of that problematic 1 plus J2 in the denominator there. And now we can start doing the same thing where we collect for like terms, in this case V1 and V2. So let's begin doing that. So V1 minus V2, make sure you're in the camera here, is equal to minus V2 over J5 minus 2V2 over 5 plus V2 over 5, that will be nice, plus JV2, times 2 over 5. And that, then we're going to have minus 4V1, and then plus 4, plus 4V2. Excellent. Okay, so this is getting quite hairy, but let's continue down our simplification journey. So let's just start saying this will be minus V2 over 5 plus J 3V2 over 5 minus 4V1 plus 4V2 equals V1 minus V2. Okay, and then finally we can then just collect our terms here. Yeah, and so we're going to have V1 minus V2 is equal to minus 4V plus V2 times 3.8 plus J 0.6. All right, now we're getting somewhere. So that must mean that minus 5 V1 plus 4.8 plus J 0.6 V2 equals 0. Whew, holy cow, that was a lot to work with, but we made it there. So then, now we can just go back to our other KCL equation, which is a reminder, was going to be 1.1 plus J 0.2 V1 minus V2 is equal to 10.6 plus J 21.2. And at this point, most of our circuit analysis is done. All we have to do now is just find a way to solve these systems of equations. Luckily, we have two values, meaning that, and two unknowns, two equations, two unknowns rather, meaning that we can solve this by solving for V1 and then plugging it in the second equation. But I'd like to take a moment and introduce something to you that you can totally use if you like, or you can use whatever method that you want to solve systems of equations. But I want to bring back some of the linear algebra that you would have learned in linear algebra and differential equations here as maybe a simpler way or a quicker way of solving these sorts of problems. So what we can do is recast the system of equations into the form of AX equals B. And we'll do that by creating a matrix A corresponding to our values for V1, V2, and then the second equation, V1, V2. And our B would just simply be a vector of size 2 corresponding to the outputs, in this case 0 and 10.6 plus J 21.2. So let's fill in our A vector, or A matrix rather. That's simply going to be minus 5, since that corresponds to the first V1 here. Then this entry is going to be 4.8 plus J 0.6. And then we've got the B taken care of. So let's go to the second KCL equation here. This V1 corresponds to 1.1 plus J 0.2. And this second entry is then simply minus 1. So now we can express this equation as a x, which x is just a vector containing values for v1 and v2 that we'll solve for, and b being the output of our equations. From there, we can rearrange this to solve for x by taking the inverse of matrix A times the vector b. So because this video is running a little bit long, I'm just going to write out our inverse vector here. You can solve this using your favorite linear algebra tool, NumPy, MATLAB, etc., or solve it yourself using determinants. This one's a little bit of a tricky one, but it is solvable by hand. This gets us 0.0604 minus J 0.6113. The other x1 value is, or inverse of the x1 value is 0.1887 minus J 0.6604. Then 0.6566 minus J 2.898. And then the last A value is going to be 0.3019 minus J 3.0566. Okay, And solving this will get us our V1 and our V2 values. So V1 is going to be equal to 68.40 minus J 16.8, leaving us with V2 equal to 68 minus J 26V. Alright, so most of our heavy lifting is now done. All we have to do now is solve using Ohm's law. Now we've got our node voltages. So now all we have to do is just solve for our currents here. Again, we're looking for currents IA, IB, and IC, and we'll need IX in order to get that for us. So let's begin with IA, which again, all we're doing here is now just applying Ohm's law. So IA is equal to V1 over 10, which is 6.84 minus J 1.68 amps. Excellent. Okay, so now if we move to IB, we'd notice that in order to get IB, we need to know this voltage here, which is a function of IX. So let's now find IX. So IX is equal to V1 minus V2 over 1 plus J2, and that is going to be equal to 3.76 plus J 1.68. Okay, so now that we got that, we can then go to IB, which is then V2 minus 20 IX over 5, which then equals minus 1.44 minus J 11.92 amps. And one last one, so IC is the last thing that we need, which is just minus V2 over J5, and that gets us 5.2 plus J 13.6 amps. So there you go. Now, this was a relatively complex example, but you notice that we can solve it just as we've been doing with normal node voltage methods and Ohm's law. This would be a heck of a lot more complicated if we had to go through and solve the differential equations in the same way. But notice here the important part is now we can solve this just using normal algebra techniques and normal circuit solving techniques that we've been learning from here on out. So really sit down, practice this problem, really get a feel for it. Because if you're able to solve something like this, then I bet anything else that we throw at you in class or in lab, you'll be more than able to do if you can tackle this circuit. But hopefully you can see what the purpose of Phasor methods is. Again, it allows us to solve circuits that we normally couldn't solve without differential equations just by using simple algebraic relations. And it makes this a heck of a lot easier than it would be than if we just had to crunch the differential equations. So all Phasor analysis really is just circuit analysis with complex numbers. And then all the other rules that you know still hold. So hopefully you find this video quite useful. If you have any questions, feel free to reach out and contact me. And with that, I hope you have a wonderful day.